Friends, welcome to my channel. Dhanesh here. In this video, I am going to discuss about Qiskit or Qiskit. Qiskit is an open source framework for quantum computing. It provides tools for creating and manipulating quantum programs and running them on prototype quantum devices or on simulators on local computer. Let's first discuss on the installation and configuration of Qiskit. See, I have Anaconda on my local system, so you can download Anaconda from you can download it easily if you type you know download Anaconda. You can get it. So it's a very important tool for artificial intelligence and even in quantum computing we are using this tool. You can download Anaconda from this link. Download the latest version. The latest version, you can see it here. It's version 5.0.0. So you can download the latest version of the Anaconda in your local machine. And here, if you see here, this is the base or root. I have TensorFlow CPU. When I install TensorFlow, it create a separate separate section for the TensorFlow. And after that, when I installed Qiskit, it's under py36. So I have to choose that. So if I want to work in TensorFlow, normally I have to select for the TensorFlow part. If I want to work TensorFlow CPU to work in Qiskit, I have to select this. So for you also, you can install Qiskit from the command prompt. See how I installed Qiskit. See cmd.exe. I can launch the Anaconda prompt. This window I can launch it from here. You can see here cmd.exe prompt, command prompt. See, this is the py36. See, if I give a, so as I have told you, the installation is, this is the command you can give, pip install Qiskit. If I run this command, you can see it here. If pip install Qiskit, yeah, it will come. So if I enter it, you can see it here. It's showing requirement already satisfied. The reason is I have already installed the Qiskit in this system. That's why I am getting it like this. Now I will tell you. So this is a simple process. It is not very complex thing. It's easy to do this. You can like NumPy, Pandas, all these things you install like that. You can do the installation. Fine. Now, what is the Qiskit textbook? You need to understand. This is a free digital textbook that will teach you the concepts of quantum computing while you learn to use the Qiskit SDK. This textbook is built on a Jupyter notebook framework that allows for easy reading, but it also allows readers to edit and run the code right in the textbook. Uh, this the code can be opened as Jupyter notebook in the IBM Quantum Experience. See, this is the Qiskit textbook. You can do the installation using the Qiskit textbook by using the this command pip install git https. See here, you need to the git command, you need to do it. So this one in the Anaconda, you can do a conda install. See, when you do conda install -c Anaconda git in this window, see for example conda install, what is that, uh, -c Anaconda Git, then you will the Git will be installed in your machine. Anaconda Git C. Then it's already installed in my machine. If Git is not there in your system, you can see this you can install. So it's already installed. After that, what you can do is you can get into this command. If you think quantum mechanics sounds challenging, you are not alone. All of our illusions are based on day to day experiences and so are better at understanding the behavior of balls and bananas than atoms or electrons. Though quantum objects can seem random and chaotic at first, they just follow a different set of rules. Once we know what those rules are, we can use them to create new and powerful technology. Quantum computing will be the most revolutionary example of this. Let's get into some practical aspects of this, quantum computation. So let's discuss this. Programming quantum computer is now something that anyone can do in the comfort of their own home. But what to create? What is a quantum program anyway? Uh, what is a quantum computer? These questions can be answered by making comparisons to standard digital computers. Unfortunately, most people uh, don't actually understand how digital computers work either. So let's understand this. We are using some Python code and we shall need to run if we want to, you should be aware of the Python code to understand this. So let's get into that. See, I have already discussed about the Qiskit textbook. So it's built on top of the Jupyter notebook we have done. Just I imported, uh, from Qiskit, I have imported the quantum circuit and I have imported the plot underscore histogram from the Qiskit visualization. If I run it, you can see here it's working fine. Now, what we are going to do, see, in any computer program, we need to convert, we need to split information into bits. The first thing we need to know about is the idea of bits. These are designed to be the world's simplest alphabet. With only two characters, 0 and 1, we can represent any piece of information. But when you talk about qubits, there are infinite possibilities. So when we talk about a classical bit, it can be either 0 or 1. So when we talk about a qubit or a quantum bit, the possibilities it's infinite. So that's the concept of superposition you may be familiar with. Superposition and quantum entanglement are the two important aspects. On top of that, the quantum computers are built. So that idea you have, I am assuming you are familiar with these concepts. So let's get into this. See, I am next time getting the widgets. Let me run this. See, you can see it here. From the Qiskit textbook.widgets, I am importing the binary widgets and n bits is equal to 5. See, these strings of bits known as binary strings can be used to represent more than just numbers. For example, there is a way to represent any text using bits. For any letter, number, or punctuation mark you want to use, you can find a corresponding string of at most 8 bits using this this. So though this qubit, so sorry, as I told you, this is how we will, all the informations are represented in the computers in terms of bits. Now we will develop our first quantum circuit. See, in a circuit, we typically need to do three jobs. First, encode the input, then do some actual computation, and finally extract an output. For your first quantum circuit, we shall focus on the last of these jobs. We start by creating a circuit with 8 qubits and 8 outputs. So we have 8 qubits and 8 outputs. That's what we are going to create. Let's see it. I have created a circuit with, as I told you, we have 8 qubits. So let me run this. See, it's working. The circuit which we have called as QZ underscore output is created by Qiskit using the quantum circuit. Now, see, the extraction of outputs in a quantum circuit is done using an operation called measure. That's very important. Quantum circuit, the extraction of output in a quantum circuit is done using an operation called measure. The operation is called measure. Each measurement tells a specific qubit to give an output to a specific output bit. So let's write. So this is the code. This is a for loop where j in range qz underscore output dot measure. I was talking about this code adds a measure operation to each of our 8 qubits. The qubits and bits are both labeled by the numbers from 0 to 7. The command qz.measure adds a measurement to our circuit qz and tells qubit j to write an output to bit j. Once again, the command qz.measure j comma j adds a measurement to our circuit qz that tells qubit j to write an output to bit j. Let me run this. See, this is the quantum circuit. As I told you, it contains 8 qubits. So you can see it here. See, qubits are always initialized to give the output 0. Since we don't do anything to our qubits in the circuit above, this is exactly the result we shall get when we measure them. So this is the simplest circuit. Now I will plot these things in a histogram. Let's see that. Let me run this. See, you can see the histogram here. So what we have done here, it is see, we can see this, we don't do anything to our qubits. This is exactly the result we shall get when we measure them. So we can see this by running the circuit many times and plotting the results in a histogram. We shall find that result is always, a 0 from each qubit. So that's what you are seeing. The reason for running many times and showing the results as a histogram is because quantum computers may have some randomness in their results. In this case, since we aren't done anything quantum, we get just 0, 0, 0 result with certainty. Now we will create an added circuit. See, now let's look at how to encode different binary strings as an input. For this, we need to we need what is known as a NOT gate. So this is the most basic operation you can do in a computer. It simply flips the bit value. NOT gate means 0 will be converted into 1 and 1 will be converted into 0. You are familiar with this. For qubits, it's an operation called X that does the job of the NOT. We call it as X. See, in the quantum computers, this X corresponds to NOT. So this is with quantum computers. This is the classical computers. So let's do the code for that. This is the code. Let me run it. See, you can see it here, the output. The code, it is QZ underscore encode. It is quantum circuit N. Now I have, QZ underscore encode dot X. X stands for the NOT gate. We already discussed. Then we have, give the method draw. So that will, give you the output here. See, extracting results can be done using the circuit we have before, QZ underscore output, so that we can do it. The circuit representation can be done. So I will show you how the circuit looks like. So this one will show you the diagram that gives the quantum circuit. So now we can run the combined circuit and look at the results. So I will show you the probabilities, how it varies. So I can show you. So this is the output. It gives the probabilities of that, how it is. See, the bit will be flipped, which comes from qubit 7, lives on the far left of the string. You can see it here. This is because Qiskit numbers the bits in a string from right to left. Some prefer to number their bits the other way around, but Qiskit system certainly has its advantages when we are using the bits to represent numbers. Specifically, it means that qubit 7 is telling us how many 2 raised to 7 as we have in our number. So by flipping this bit, we have now written the number 128 in our simple 8-bit computer. Now try out writing another number for yourself. So you could do your age, for example, just use search engine to find out what number looks like in binary, and then add zeros to left side of if you are younger than 64. See, let's write another. So let's run this. See, you can see it here. So as I told, the X stands for the NOT gate. In quantum computers, X is the NOT gate. So now we know how to encode information in a computer. The next step is to process it, to take an input that we have encoded and turn it into an output that we need. Let's add something. So how we do the addition? So basic math, in you know how to add two numbers, but see, the process here is we need to convert it into binary and then add it, and again convert, decode it to the decimal number system. You are familiar with that. So adding with Qiskit. See, let's make our own half adder using Qiskit. This will include a part of the circuit that encodes the input, a part that executes the algorithm, and a part that extracts the result. The first part will need to be changed whenever we want to use the new input. So the two bits we want to add are encoded into the qubit 0 and 1. So let's do that. So first input, this is the second input. Input 1 and input 2. So this is the first input and the second input. When you give in the exclusive OR 0, 0, you will get 0. When you give 0 and 1, you will get 1. 1 and 0, you will get 1. And 1 and 1, you will get 0. This is the exclusive OR, the truth table for the exclusive OR. You are familiar with this. So this is the truth table for the exclusive OR. Fine. So let's do this. How we can do this? Let's write the code, and I will run this. So yeah, you can see it here. We have the 0, and as I discussed, we are using 2 qubits. See, you have seen that Q0 and Q1. So this is applied to a pair of qubits. One acts as the control qubit. This is the one with the little dot you can see here. The other acts as the target qubit. That is the with the big circle. There are multiple ways to explain the effect of the C naught. One is to say that it looks at its two input bits to see whether they are the same or different. So try the C naught out for yourself by trying each of the possible inputs. So for example, a circuit that tests C naught with input 0, 1. Like computer science, the controlled NOT gate is a quantum logic gate that is an essential component in the construction of a gate-based quantum computer. It can be used to entangle and disentangle EPR states. In computer science, the controlled NOT gate, the C naught, is a quantum logic gate that is an essential component in the construction of a gate-based quantum computer. It can be used to entangle and disentangle EPR states. You may be familiar with EPR state. EPR states means Einstein, Podolsky, and Rosen state. See, any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of C0 gates and a single qubit rotations. Execute this circuit, you will find that the output is 11. We can think of this happening because of either of the following reasons. The C0 calculates whether the input values are different and finds that they are, which means that it wants to output 1. And this is the output. So here you are giving 0, 0, 0, 1, 1, 0, 1, 1, and you will get 0, 0, 1, 1, 1, 0, and 0, 1. This is the input and the output. See, for our half adder, we don't want to override one of our inputs. Instead, we want to write the result on a different pair of qubits. For this, you can use the C notes. C notes I already discussed. See, let me try. Let me run this. See, you can see this quantum circuit here. This is the output. It's here. Now halfway to a fully working half adder. We just have the other bit of the output left to do, the one that we will leave on qubit 3. If you look again at the 4 possible sums, you shall notice that there is only one case for which this is 1 instead of 0. To calculate the pair of the output, we could just get our computer to look at whether both the inputs are 1. So for this, we need a new gate like a C naught. C naught is the controlled NOT gate, on the qubits instead of just one. This will perform not on the target qubit on both the controls are in state 1. The new gate is called the toffoli. So the toffoli, for those if you are familiar with Boolean logic gates, it's basically an AND gate. Toffoli gate is basically an AND gate. Logic circuits, the toffoli gate, also CC NOT gate. We call it as the known as CC NOT gate. This is the toffoli gate, invented by Thomas Toffoli. Uh, is a universal Thomas toffoli. It's a universal reversible logic gate, which means that any reversible circuit can be constructed from toffoli gates. It's also known as the controlled NOT gate. Previously, we have the C NOT gate. This is CC NOT gate. It's known as the toffoli gate. It's known as the controlled NOT gate, which describes its action. It has a 3-bit inputs and outputs. The first 2 bits are both set to 1. It inverts the third bit, otherwise all bits stay the same. So that is known as the toffoli gate. The input, if it is 0, it will be 1, and if it is 1, it should be 0. So the toffoli gate, when you give um, the input both 0, it would be 0 0, 0 1, the output will be 0 1, 1 0, it would be 1 1, and 1 1 as the input, it would be 1 0. So you can see it's working. If you see the code here, uh, you can see it here. See the toffoli is represented with the ccx command. You can see it here, ccx command. So the normal cx denote the C nodes are the CX represents the C node, and CCX to write the AND if the inputs on qubit 3. See here the inputs in qubit 0 and 1, it is encoded, and after that we have the exclusive OR gate, that is the C nodes. Then we have the CCX, that is the toffoli gate, and it write the AND of the inputs on qubit 3, and we have the output, it is shown here. So you can see it here. So in this example, we are calculating 1 plus 1 because the two inputs are both 1. Let's see how we get the outputs. So I'm, the histogram, you can see it here. See, this is the output here. So we are calculating 1 plus 1 because the two input qubits are both 1. So this is what we are getting. The result is 10, which is the binary representation of the number 2. We have built a computer that can solve the famous mathematical problem of 1 plus 1. Now we can try it out with the other 3 possible inputs and show that our algorithm gives the right results for those 2. The half adder contains everything you need for addition with NOT, C NOT. So we used 3 gates here. The C NOT gate, that is the controlled NOT gate. Then you have the toffoli gate, that is, we call it as the CC NOT gate. It is known as the CC NOT gate. Controlled NOT gate, that we call it as the toffoli gate. This is known as toffoli gate. So these are all the gates we used here. So one more thing I am, just telling you the version of the Qiskit by using this, piece of script. So I'm writing this. Let me run this. See, you can see the Qiskit Terra, Ignis, Aqua. See all the versions it's given here. So this is a a simple introduction to Qiskit and how you can, use the Qiskit. I have discussed some idea about the basic gates as well.
Thanks for watching. Please like, share, and subscribe. Thanks a lot.